So we're going to get started on the chemistry of life. We're going to take about 30 credits of chemistry, and we're going to try to squeeze it into one chapter in one textbook. So if you feel like we're going kind of fast right now, we are, and that's okay. We're going to focus on a very shallow level of understanding right now. We aren't going to spend lots and lots of time talking about the minutia of each individual topic. So if one specific thing is confusing to you in this chapter, I would encourage you to not stress out too much about it. Instead, focus on the big picture for this chemistry chapter. So if we look at what we're made out of, the stuff that we're made out of, generically, is referred to as matter. Matter is anything that's going to have mass to it, and the building blocks for matter are our elements. These elements that we're made out of are going to differ in chemical composition from each other. Now, if we look at the other side of the room, we have the periodic table of the elements showing all of the elements that were known at the time. There's been a few more added to the bottom, like the 113, 115, 117, since that periodic table was printed. And those elements are defined by the fact that we can't simplify them. We cannot break them down by any chemical means. We physically can break down a gold atom into smaller, simpler elements. But chemically, through chemistry, we can't turn gold into anything else. Or, more irritatingly for alchemists, there's no way to use chemistry to turn lead into gold. But if you had an atom smasher, theoretically you could do it physically. It just wouldn't be worth it. And if we take these elements, these chemicals, these basic building blocks of life and matter, and we chop them into small pieces, the smallest piece of any element that we can have is one individual atom. That atom is defined by its ability to retain the chemical properties of that element. So the smallest piece of gold that is shiny like gold, the smallest piece of gold that has the electrical and chemical properties of gold, is going to be one atom of gold. If we go any smaller than that, we start to lose the chemical and physical properties, and we no longer have an atom of that element. We now are going into the subatomic, or smaller than the atom, scale. If we take these atoms, or multiple atoms, and we bind them together, or hold them together, we call that a molecule. Generally speaking, any molecule is made of two or more atoms held together by a chemical bond. And there are multiple kinds of chemical bonds. The two that we're going to focus on mostly in this chapter are covalent and ionic chemical bonding. Has anyone in here taken a chemistry class before? Can we remember any of the other chemical bonds that are out there? Just to poll the audience. Not so much? That's okay. I'm not even going to take time to mention them because they aren't in this chapter. So if we look at our periodic table, there's some basic information that we can glean from this periodic table. One is the atomic symbol. That's the abbreviation for the element. Our atomic symbols are one or two letter atomic symbols. When we look at these atomic symbols, sometimes they'll be one letter, sometimes they are two letters. As a rule of thumb, the first letter is always capitalized. And if there is a second letter, that second letter can be lowercase. Usually the abbreviation is going to be based off of the name directly, the English name of the element. So H is for hydrogen, He is for helium. And most abbreviations make sense. Mg for magnesium, Ca for calcium, but a couple abbreviations are a little bit confusing. And that's because those abbreviations are based off the Latin or Greek names for the elements. And those are for the old school elements that were isolated a long time ago. For example, the abbreviation for sodium, which in English starts with an SO, is not SO. Instead, it's Na because of the Latin word for sodium, which is natrium. Or if we look at the abbreviation for, do we have it up here? Iron was the other one I was going to show for us. We don't have iron on the screen, so I'll just draw it up here. The abbreviation for iron is Fe, And unfortunately, that's based off of the Latin name for ferric, or the old name for iron. But most abbreviations are based off the English name and are fairly intuitive. We are not going to assign any sheets for you to memorize. This is not a chemistry class, so don't spend time memorizing the periodic table. I want you to be able to use a periodic table. If we look at this periodic table, we're also going to have information in terms of the composition of the individual elements. And this information is given in terms of atomic mass and atomic number. Our atomic mass tells us the number of a specific subatomic particle, specifically the number of protons in the element. And I'm going to use a P with a plus sign to abbreviate for protons. So the atomic number and atomic mass are based off our subatomic particles. Atomic mass is the number of protons combined with the number of neutrons. And the atomic number is just the number of protons in the element. Now, if you change the number of neutrons in an element, if you increase or decrease the number of neutrons, you're not going to be changing the atomic number. The atomic number is only going to be based off of the number of those protons in the element. And if we look at our periodic table, it's arranged by atomic number. Older periodic tables used to be arranged by atomic mass, but we found that it actually works better if we use atomic number compared to atomic mass. Our atomic number is on the top of each cell on this periodic table. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we skipped a bunch that were off to the left there, excuse me, off to our right. So we arrange our periodic table by increasing atomic number. Oftentimes students ask me, how come atomic mass has a bunch of decimal points on it? The reason atomic mass has a bunch of decimal points on it is because on our periodic tables, different elements or different atoms of the same element can have different numbers of neutrons. So sometimes a lithium atom can have 6 neutrons in it. Sometimes lithium atoms have 4 neutrons in them. Sometimes they have 3 neutrons in them. And we take the number of neutrons in all these different lithium atoms and average them together, in addition to the 3 protons that are in lithium. And because we average together the differing number of neutrons, we end up with some decimal points after atomic mass. So on a periodic table, this is actually average atomic mass, because there are different kinds of the same element with different specific atomic masses. Any questions about that? All right, well, let's keep moving on. If we look at those particles that make up the atom, a term that's often used to describe them is subatomic. And I remember the first time I taught chemistry, my students were super intimidated by the term subatomic. So let's spend some time just talking about that word, so hopefully it's less intimidating. The word sub is a prefix that means what? For those of you who've looked at your midterm sheet, what does that prefix sub mean? It means smaller. So the sub means smaller. What is it smaller than? It is smaller than an atom. So a subatomic particle is a particle that is smaller than an atom. That's all that word means. And the 3 subatomic particles that we're going to focus on are neutrons, protons, and electrons. Those are the 3 that I want you to focus on. There are more, but we aren't going to cover them in this class. Neutrons are neutrally charged, hence the name neutron. And because neutrons are neutrally charged, they traditionally have been the most elusive subatomic particle. They're the most difficult one to isolate because they never interacted with strong magnetic fields or strong electrical fields. These neutral neutrons are going to be located next to the positively charged protons. Both the neutrons and the protons are going to be in the middle or the center of the atom. The term for the center of an atom is the nucleus. And in that center of the atom, we have the two different kinds of subatomic particles, the protons and the neutrons that we've talked about so far. Now, if I were to give you an analogy or a good scale of reference or frame of reference for how the atom is organized, if we were to have a neutron that is the size of a nucleus that is the size of a poppy seed, so really, really tiny, but still big enough that you could see it with your naked eye, the entire atom would be about the size of a Lambeau Field, or about the size of a football stadium. So the atom is relatively enormous compared to the size of the nucleus that contains the protons and neutrons. Outside of that nucleus in the center of the atom that contains the protons and the neutrons, we have the third subatomic particle, the electron. And this electron has a negative charge to it and is located outside of the nucleus or around the nucleus. So in the middle of the atom, we have protons and neutrons, and then on the outside of the atom, or on the edge of the atom, we have the electrons. So if I was to randomly grab a subatomic particle from the outside or edge of an atom, what charge would that particle have to it? It would be a negative charge, because it would have to be an electron on the outside or the edge of the atom. And then when we have chemistry occurring, generally speaking, we're going to be adding electrons to an atom or subtracting electrons from an atom. Chemistry can sometimes be defined as the movement of outer electrons from one atom to another atom. So we will shuffle these electrons around. Now, if we were to look at a simple hydrogen atom, that simple hydrogen atom has one proton in its nucleus and 0 neutrons in its nucleus. So if we have one proton and 0 neutrons, what would the atomic mass be of that hydrogen atom? 1 plus 0 gives us just 1. So the atomic mass of that hydrogen atom is going to be 1. How about the atomic number? What did we define the atomic number as? The number of protons. So the atomic number for this hydrogen atom would be what? Just 1. Now, as we work with larger and larger atoms, we're going to have more protons, more neutrons, and more electrons in these atoms. Generally speaking, if we're working with an atom that does not have an overall charge or an overall electrical charge to it, there's going to be an equal number of protons and electrons in the atom. And on the screen, these little blue dots represent electrons on the outside of the atom. So for this carbon atom, right here, we have 6 protons in the middle, and then 6 electrons on the outside. And the positive charge from the proton cancels out the negative charge from the electron. So we have an equal number of positive charges and an equal number of negative charges. The atom overall has a charge of 0. If we look at oxygen on the lower right corner of your screen, we have 8 protons and 8 electrons, an overall charge of 0. So, any questions so far about atoms? All right, let's keep going. Now, depending on the specific number of neutrons in the nucleus, we can have a different kind of atom of the same element. To change an element, we change the atomic number. We change the number of protons in the nucleus. So that if we have hydrogen atoms, all hydrogen atoms, by definition, have to have exactly 1 proton in their nuclei. But we can change the number of neutrons in the nuclei and still have a hydrogen atom. We can still keep the number of protons the same. As we increase or decrease the number of neutrons in the nucleus of an atom, we change the specific isotope that we're working with of that element. So we can have, for example, hydrogen 1, hydrogen 2, and hydrogen 3. We can have a hydrogen atom with an atomic mass of 1, hydrogen with an atomic mass of 2, and hydrogen with an atomic mass of 3. Each one of those hydrogen atoms has exactly one proton in its nucleus. They're all hydrogen. They all have the same atomic number, but they have differing numbers of neutrons. We've already talked about hydrogen 1 on the last screen. Hydrogen 1 has 1 proton and 0 neutrons in its nucleus. Hydrogen 2 has an atomic mass of 2. 1 proton, 1 neutron. How about hydrogen 3? How many neutrons are in hydrogen 3? 2. Very good, Austin. So hydrogen 3 has 2 neutrons and 1 proton in its nucleus. So by changing the number of neutrons, we can change the atomic mass. We can change the isotope of the element that we're working with. Some isotopes are really stable and can exist for a very long time. Other isotopes are very unstable, and they give off radioactivity. A good example is carbon-12 versus carbon-14. You probably heard of carbon-14 in the news or in the science article that you read when someone was talking about radiometric dating or carbon-14 dating of a fossil that was dug up. Carbon-14 has an atomic mass of 14, and it's radioactive. It will decompose into carbon-12, which is a stable isotope of carbon. Carbon-12 is not radioactive and will exist for millions and millions of years without changing. In healthcare, we can use radioactive isotopes for medications. If somebody is receiving radiation therapy, generally speaking, they are going to be blasted with radiation from a radioactive isotope that can then kill cancerous cells by pointing the beam of radiation at a cancerous tumor. We can also use radioactive isotopes to figure out how old something is, or we can use radioactive isotopes to figure out what's happening on the inside of the body. In those situations, you would give the patient a glass or a beverage that contains radioactive sugar, and they would drink the radioactive sugar, and then the parts of their body that have a really high metabolism, that use up energy really quickly, would suck up lots of that radioactive sugar and glow bright on the scan when you scan their body. And parts of their body that have a really low metabolism, that don't use up lots of energy, would be very dark when you scanned them. Usually in those situations, the cancer tumors that are growing really quickly absorb lots of the radioactive sugar, and parts of the body that don't grow quickly, like your bones or your adipose tissue that have low metabolism, hardly absorb any of the radioactive sugar. Any questions about radioisotopes? Okie dokie. Sometimes that radiation can be harmful. Generally speaking, the radiation that you're exposed to on an everyday basis, from the sun, from the room you're sitting in right now, is at such a low concentration, you don't need to worry about it. Here's some random trivia for you. When you smoke a cigarette, you are exposed to more rads of radiation than you are when you receive a full chest X-ray, because tobacco preferentially absorbs radioactive isotopes from the ground. You also get more radiation from a cigarette than you would by standing next to the cooling towers at the radioactive or the nuclear power plant here in town. If you receive a high dose of radiation, though, that higher dose of radiation can cause damage to your genome or your genetic code, your DNA. And as those small bits of damage build up in our body, in our genome, eventually the cells can become cancerous and start growing into tumors. And at that point, we would have a cancer, which is a problem for most people. Here's an example of some PET scans that were performed for positron emission topography, PET scan. And these patients drank some radioactive cocktails, and they found in this patient that her thyroid gland lit up bright like a Christmas tree, and the physician can notice by looking at the screen that the patient is missing a portion of her thyroid gland. This patient drank the radioactive cocktail, and that cocktail was absorbed by the brain tissue and caused their brain to light up very bright. And we can see that parts of the brain are more active and parts of the brain are less active, depending on what the patient was asked to do or think about while they were being scanned. As we take these atoms that we're made out of and we mix and match them and we start joining them together, we start to make molecules. A molecule, generally speaking, is made of two or more atoms that are bonded together. And as we bond them together, we use those chemical bonds that I had mentioned earlier. Now we can take two atoms that are the same element and attach them together, or we can take atoms from different elements and attach them together. There's no hard and fast rule about what elements we're attaching to each other. As long as we have two or more atoms, we have a molecule. Some molecules have 10 atoms in them. Some molecules have 1,000 atoms in them. Most of the ones that we're going to talk about have less than 5 atoms in them, just because they're easier to wrap your mind around. If we are looking at a molecule that's made of a special kind of atom that has lost or gained electrons, that molecule is going to be held together with an ionic bond. Sometimes it's referred to as a formula unit instead of a molecule. That's a fine pedantic nuance that we're not going to spend a lot of time talking about in this class. If we have an ionic bond, it's a chemical bond that's formed when one atom takes an electron and another atom donates an electron. And as an atom gains an electron, it's going to have an electrical charge change to it. Electrons have what charge, class? They have a negative charge. Very well done, Austin. So if I gain one more electron, what have I done to the overall charge? Have I caused it to go up or down or stay the same? If I add negative charges, if an atom's gaining negative charges, what happens to the overall charge of the atom? So let's say I have an atom, and it starts with 1 proton and 1 electron. And if I add an electron to it, what happens to the overall charge of the atom? Does it go up and become more positive? Does it go down and become more negative? Yeah, it goes down, it becomes more negative. So that atom that receives the electron has a negative charge, or becomes more negative. And then the atom that loses the electron, let's say the atom started with 1 proton and 1 electron, but then it loses the electron, that atom that lost the electron becomes more positively charged. And once these atoms have charges to them, we can call them ions. And they can be held together with an ionic bond. You could think of it as a positive charge being attracted to a negative charge.
So
They do not affect it directly. Why would they not affect the ionic bond directly? Bingo, well done, Austin. So neutrons don't affect the positive or negative aspect or the charge of an atom, so the number of neutrons aren't going to influence the strength of the ionic bond that forms. The number of neutrons is going to determine whether or not the element is radioactive or not. Any other questions about ionic bonds or ions while we're on this slide? Okie dokie. So here in this figure, we can see a sodium atom and a chlorine atom. These are the classic examples for ionic bonds. This sodium atom can donate 1 electron to the chlorine atom. And now the chlorine atom that's gained 1 electron has an overall negative charge now. The sodium atom that's lost the 1 electron has an overall positive charge to it now. And a positive will be attracted to a negative. And all these positives and negatively charged atoms will form ionic bonds and stick together and form sodium chloride crystals, which we use as table salt. A covalent bond, on the other hand, is much stronger than an ionic bond. An ionic bond forms when we transfer an electron from one atom to another atom to make ions. A covalent bond is formed when we share an electron between atoms. So instead of transferring it, it's shared and used by both atoms at the same time. Because they're used by both atoms at the same time, each atom is going to hang on very tightly to the electron, and consequently, those atoms are going to stick together with a lot of force. There'll be a strong chemical bond holding those atoms together. So if I was to look at one oxygen atom and two hydrogen atoms, we can share electrons between these atoms. This electron can be donated to the top hydrogen, and our second electron can be donated to the bottom hydrogen. So this hydrogen can gain an electron on the bottom, our hydrogen on the top can gain an electron, and both of those electrons are going to be from the oxygen. But it's not like the oxygen is losing its electron. The oxygen is sharing its electrons. So we will have the one electron being shared between the hydrogen and the oxygen, our blue electron, and our red electron can also be shared between a hydrogen and an oxygen. The hydrogens are also going to share their electrons as well. So the sharing is a two-way street. It's not one-sided, it's a two-sided sharing. So we also are going to share electrons from the hydrogens to the oxygen as well. And when they are all sharing their bonds together, we have a much more stable configuration, and we'll have covalent bonds in this situation because instead of transferring, we are now sharing the electrons. Questions about ionic and covalent bonds? Okie dokie. So, guys, gals, help me out here. What kind of chemical bond is the strongest? Would it be covalent, ionic, or neither? They're both the same in strength. That's right, covalent. Covalent is definitely going to be our strongest chemical bond. So, let's move on and start talking about that water molecule that we made on the last PowerPoint slide. What kind of chemical bonds hold water molecules together? What kind of chemical bond holds the hydrogen to the oxygen in the water molecule? It was 2 slides ago in the PowerPoint. A covalent bond. Excellent. So these water molecules are held together by covalent bonds, and please have this memorized. You probably do already. The chemical formula of water is what? H2O. Excellent. I had an English prof in college who said the chemical formula was HO2. And I remember my classmates and I were just like, oh, English prof. It's okay. I misspell words in English all the time, and they probably shake their heads at me for that. Something that's very cool about water is that it's a liquid at room temperature, but if we cool it off slightly, it becomes a solid, it becomes ice, and if we heat it up slightly, it becomes a gas. Water is very unique in that it exists as solids, liquids, and gas on our planet at different parts of our planet at different times. And that makes it a very unique chemical compound. Something else that's unique about water is it changes temperature very slowly. How many of you have ever watched a pot of water boil on the stove? And it takes forever, darn it. That's a good example of how water changes temperature very slowly. So if we were to look at our bodies, we're made of mostly water. And that means that our body temperature is going to change very slowly over time compared to other things in the room. For example, if you were to sit in the room with a piece of metal, the piece of metal, generally speaking, changes temperature super duper quickly compared to our bodies, which are mostly water. Water also has a high heat of evaporation. And that's kind of a technical term, so let's break that down. This high heat of evaporation means that when we go from a liquid to a gas, when we change states of matter from a liquid to a gas, it uses up lots of energy. So this means if you're sweaty and that sweat on the surface of your body evaporates off, the water evaporates off your arm, it's going to take lots of heat energy with it and help cool you off very quickly. Other chemicals like alcohol or acetone have much lower heats of evaporation and don't take as much energy with them when they go from a liquid to a gas. Another characteristic of water is that when we freeze it, it's less and make it into a solid, its density decreases. And this is unique in that most chemical compounds are more dense when they're solids and less dense when they are liquids. Water is an exception to the norm. Solid water is less dense than liquid water. One of the wonderful properties about this is that solid water, that frozen water, will rise to the surface of a lake or a stream and then protect the surface of the water and insulate it during winter months so that in a pond or a stream during the winter, the warmest point will always be at the bottom of the pond. Our water molecules also cling together tightly, and I'm not talking about the covalent bonds that hold the atoms together within a molecule. I'm talking about a different chemical bond that holds separate water molecules together. And this special chemical bond is called a hydrogen bond, and water molecules have lots and lots of hydrogen bonds that hold them together. It's the reason that it hurts when you belly flop off a diving board. You aren't breaking covalent bonds, you're breaking hydrogen bonds. And the force required to break those hydrogen bonds is enough force to cause you to get some bruising and tenderness from belly flopping. And then finally, water is known as a universal solvent. In particular, water can dissolve polar molecules very easily. So if we were to think of a polar molecule is anything that has regions of different charge. So instead of having a uniform electric charge across the entire molecule, one region can be more positive and another region can be more negative. A good example of that is sodium chloride, table salt. It has positive and negative charges in it, and there are ions making up those ionic bonds. So table salt, since it's an ionic compound, dissolves really, really well in water. All ionic compounds, as a rule of thumb, can dissolve in water because they have those polar charges, which water is ideal for solvating or dissolving. If I was to look at one individual water molecule, it has 2 hydrogens and 1 oxygen. And on this screen, our hydrogens are white and the oxygens are red. In our water molecules, we have covalent bonds holding the atoms together where we share the electrons between the atoms. But the water molecule doesn't do a good job of sharing electrons. Oxygen's a little bit more electron greedy than hydrogen. So oxygen will take more than its fair share of electrons and have a slight negative charge to it, a partial negative charge. And usually that's going to be represented with a delta minus, which you can see right there in very small print. So in water molecules, the oxygens have a partial negative charge, and then the hydrogens have a partial positive charge. And the partial positive charge of a hydrogen is going to be attracted to the partial negative charge of an oxygen of an adjacent water molecule. And this weak attraction between molecules is what we call a hydrogen bond. And because water molecules are only partially positive and partially negative atoms, they are ideal for having the maximum number of hydrogen bonds. Any questions about hydrogen bonds or water molecules yet? If we were to compare covalent bonds, ionic bonds, and hydrogen bonds to each other, the strongest is going to be the covalent, then we'll have ionic, and then at the weakest of the 3 is the hydrogen bond itself. In our water molecules, we can have ions dissolved or polar compounds dissolved. Sometimes we're going to have a chemical dissolved in the water that adds hydrogen ions to solution, or a positively charged hydrogen atom. Any chemical that puts more hydrogen ions in solution is an acidic chemical compound. On the flip side of that, any chemical compound that removes hydrogen ions from the water solution, or that adds hydroxide ions, OH minus ions to solution, is a basic or alkaline compound. And these acids and bases will work opposite of each other. Can you, class, think of any acids that you work with in your everyday life? Either in your body, or in your cleaning cabinet, or in your car, or maybe at work. We have amino acids, absolutely, and we use those to make proteins. We also have stomach acid that we use to help digest food. Or if you're looking at your car, there's sulfuric acid in a lot of car batteries. So these acids are all over our lives. We generally speaking don't think about when we use them though, because we aren't using them in concentrations that are harmful to us. On the flip side, we also use basic compounds all the time. For example, seawater is slightly basic, our blood is slightly basic, or bleach or ammonia cleaner are all slightly basic chemical compounds as well. To measure how acidic or how basic a solution is, we use a chemical scale called the pH scale. Now, a bad analogy is to think of the pH scale as the power of hydrogen, where we have a more powerful hydrogen solution or more hydrogen ions in solution, it'll be more acidic. And if we have fewer hydrogens in solution, it's more basic. This P actually is a mathematical symbol that stands for some logarithmic math that we're not going to go into in this class. But if we have more hydrogens in solution, the pH is going to be lower. And if that pH drops below the level of 7, we define the solution as acidic. But if we remove hydrogen ions from solution, the pH starts to increase. And if it increases above 7, we call the solution basic or alkaline. In most situations, you're going to work with pHs that are close to 7. Maybe you'll go with something as low as 3 or something as high as 10. A good example of something that's as low as 3 would be lemon juice. That has a pH of about 3, or coffee has a pH of about 4. If we looked at bleach from the cupboard that's been undiluted, that has a pH of about 10-ish. If you're working with a really strong acid, it'll be less than 3 for its pH, or a strong base is greater than 14. The strongest acid I've worked with was negative 1.3 something. So it was scary strong, and I had lots of personal protective equipment on. On the same token, the strongest base I've worked with was a pH of about 15. And again, that was a scary strong base. So I had lots of goggles, gloves, a gown, face shield, the whole 9 yards. When we go from a pH of 6 to a pH of 5, the solution becomes 10 times more acidic. This pH scale is a logarithmic scale, which means every time we change one number on the pH scale, we change the concentration tenfold. So if I was to go from 6 to 3 with my pH, a solution with a pH of 3 is 1,000 times more acidic than a solution with a pH of 6, because I've moved 3 points on the pH scale. So 10 times 10 times 10, 1,000 times. So if we were to think of pure water, which has a neutral pH, and lemon juice, which has a pH of about 3, lemon juice is about 10,000 times more acidic than pure water. If you're working around the house, another good rule of thumb is that acids are tart. Most of the fruits and vegetables we eat have some acids built into them. Think of like citric acid or ascorbic acid. And if you're working with a basic compound, it's usually slippery to the touch and very bitter tasting or poisonous. Many plants will produce alkali or basic poisons to help make insects die when the insect starts eating the plant. You can think of caffeine or nicotine. Those are two classic examples of basic poisons produced by plants to help kill insects. So here's our pH scale. We can see pure water at a pH of 7. We have vinegar at pH of 3. And I was wrong. Lemon juice is actually a pH of 2. I was off by an order of magnitude, or times tenfold. And then we can have very basic chemical compounds. So right about here with household bleach, that's about as basic as you'll want to go in your house and touch it with your bare hand. You'll still want to clean your hand up very quickly. If you are working with Drano or concentrated drain cleaner, that's going to be a pH of about 14, and it'll consist mostly of sodium hydroxide. So, class, if I decrease the amount of hydrogen ions that are dissolved in an aqueous solution, or that are dissolved in water, what have I done? So I'm removing hydrogens or decreasing the ions and hydrogen ions in solution. Have I added an acid to the solution? Have I made the solution more acidic? Did I add water to the solution? Or did I make the solution more basic? Austin, I want you to let the ladies answer this one, because you've been answering a lot of questions. So if I remove hydrogen ions from solution, what am I doing? So I have fewer hydrogen ions. What is an acid? An acid is anything that does what? That adds what to solution? Excellent. So acids add hydrogen ions to solution. And if I'm removing hydrogen ions, I am definitely not adding an acid. I'm making it more basic. Well done. So if I remove hydrogen ions from solution, I am making that solution more basic.